welcome to the algorithm seminar. Today we're happy to have Muhammad to give a talk. So Muhammad Osama is a PhD candidate advised by Professor John Owens in the Electrical and Computer Engineering Department at the University of California, Davis. Muhammad's current research focuses on general purpose GPU computing, GPGPU, specifically GPU load balancing for dense and sparse workloads. He's also the lead developer of Gunrock, a GPU graph analytics library, and has been a part of DARPA's Hive and SDH projects. Muhammad graduated from the University of Washington, Seattle with a bachelor degree in electrical engineering with a research focus on real-time graphics. And today he's going to talk about expressing high-performance irregular computations on the GPU. Please welcome our speaker.
Awesome, thank you. Good to see some familiar faces here, and thank you guys for having me today. My name is Mohammed. I'll be presenting expressing high-performance computation on GPUs. Hopefully the slides are good. Some of the stuff that I've worked on in the past and currently also working on are programming model for a load balancing framework on GPUs, which is sort of the core underlying optimization that leads to high performance for irregular workloads like graph analytics and sparse linear algebra and similar workloads. I've also been the lead developer on Gunrock and also on Essentials, which is sort of a derivative project of Gunrock, simplifying GPU graph analytics. I've also done a lot of work on general matrix multiplication. I partnered with NVIDIA, sort of scheduling how to schedule dense linear algebra work on GPUs, and a lot of my research is focused around sort of scheduling, mapping, load balancing, etc. I've also worked on DARPA Hive Challenge, which is something maybe some of the graph folks would be interested in, where we did 10 real-world graph algorithms on using Gunrock. We built these 10 algorithms that were important to DARPA and some of the government folks, and these were interesting problems that they sort of cared about. Today, I'll be sort of focusing on expressing irregular parallel workloads more from sort of the GPU graph analytics direction. I will somewhat dive into my load balancing work as well. But if you have any questions on any of the stuff that I talk about and you would want to have a detailed chat, I'll be sort of happy to do that. But this talk will mainly focus on the abstraction and sort of the API level rather than more of the algorithm side of things. But if you guys are curious about the underlying algorithms and how things actually function and really get implemented at the lower level, I'll be happy to talk about that as well. I am a CUDA C++ programmer, so I've worked deeply within the hardware as well, and all the way through the software stack in building these libraries and workloads. So GPU graph analytics so parallel GPU graph analytics is usually sort of represented using two programming models. One I describe as a data-centric programming model, which is sort of the primary approach that Gunrock takes, where data is the first-class citizen, operating directly on we operate directly on the vertices and edges and components of the graph itself, and sort of transform them, traverse them, and so on. And this abstraction generally deploys two main programming models, which I'll describe more in detail. But one of them focuses on this bulk synchronous programming model approach, and the other one is asynchronous programming model. And we'll go through them in a second. But the other side of how to express graph analytics is using the sparse linear algebra world. This is mainly stuff done by Graph BLAS folks and that community, which I'm also very involved with. And this focuses around representing graphs as linear algebra and operations. So you represent graphs as sparse matrices, and then perform linear algebra operations like sparse matrix vector multiplication to implement algorithms like breadth first search and single source shortest path. In today's talk, I'll be mainly focusing on the data-centric model, and maybe later in the talk when I talk about load balancing, I'll discuss some of the sparse linear algebra workloads. But the data-centric sort of side fascinates me a bit more. The ideas I talk about today are applicable to sort of both approaches to graph analytics. So my favorite way to sort of discuss this idea, this concept of data-centric GPU graph analytics is using a very simple example. And as we sort of walk through this example, we'll identify some of the key components that are sort of important to these ideas and how they get implemented in actual real-world frameworks that target GPUs. And a simple example that we can take here is single source shortest path. This is literally out of the CLRS Introduction to Algorithms book, where we'd want to find a single source shortest path for a graph problem. Hopefully, that's sort of a simple enough problem that we could gather some of the key ideas from. And my goal would be to quickly sort of walk through the pseudo algorithm and then identify some of the key components that I'm discussing. I'll be discussing later in the presentation, and sort of how they get mapped onto the GPUs. So if you look at some of the components of the pseudocode for Sssp, one of the main sort of steps that repeats across multiple algorithms is just like an initialization stage. It's very common in graph algorithms. You would like to initialize your problem. Maybe for some graph problems, it's setting the distance for a source node to be 0 and setting all the other distances for all the other vertices to infinity. And there could be other ways to sort of initialize the problem as well. But preparation of data is usually one of the most basic, like the first step that you kind of do. The more interesting side of things is the condition. It's often described as a relaxation step or relaxation condition. It's sort of a condition that you apply on any traversal or transformation. That's how I perceive it. And in this pseudocode, what we're attempting to do is, if you have found the new minimum shortest path, we update the shortest path of all sort of the vertices and of the vertex that's being processed. So the key idea here is that there's some sort of condition applied to the traversal or transformation of the graph, of the vertices, of the edges, and sort of components of the graph within them. And these conditions show up all over graph analytics. It's kind of how you identify. It's up to sort of the user to identify these and implement them in certain ways, or try to take an approach that sort of capture these conditions. And sort of the last step that encapsulates all of this together is how you schedule sort of the work of your graph algorithm, like how you put these individual components together to build a complete algorithm. For the Sssp example that we're looking at, we sort of take the initialization step and stick it at the top, sort of the first step to sort of initializing it. The other key ideas that we want to notice is here is in creating this sort of algorithm, we have a loop that loops over and does some amount of work, and this loop is sort of infinite until a certain condition is met. So in this case, it's saying that while my queue is not empty, keep doing work, keep doing this work that I've described. And taking a quick look at that work, it seems to be you extract sort of the minimum vertex, put it in a set, process that set, and find apply the relaxation condition when you're doing the traversal. So some key ideas that we can take away from this entire sort of schedule and this algorithm are, there is a notion of active working set. So there are some vertices that are actively being processed and being worked on. There's a notion of a while loop, a main loop that's sort of putting things together. There is a key idea around a convergence condition. So there's some condition that's being met that's telling you that the graph algorithm is now complete. Let's stop processing. And then finally there's some operation on the vertices or edges or components of the graph. In this case, that's this for each vertex in the graph, in the sort of the adjacency list of that vertex U. By the way, if you have any questions, feel free to interrupt me and ask questions. But what we're attempting to do with this sort of pseudo algorithm is just identify these key components and then take a closer look at them. So we can put them together in what I call some of the essential components of GPU graph analytics for the data-centric model. The first one being how a graph is represented, or the graph itself. So in our case, it's just vertices and edges, and it could be the underlying representation could be many different data structures. It could be represented in the dense form. It could be represented in many of the sparse formats that exist out there. Like if you're aware of CSR, compressed sparse row, or coordinate format, adjacency list, and so on. The initialization step I talked about, so some preparation of data. The idea of an active set of items to process is very, very important, and I'll come back to that in a second. Some operations that process that work on that active set, a convergence condition, and a main loop. So this slide sort of just summarizes those key components that we have identified from the previous example. So let's take a look at the idea of an active set. So in Gunrock's programming model, that active set is called a frontier, and I believe that's true for many of the other frameworks as well. But a frontier, you can think of it as simply as a data structure that holds that active set that we were discussing earlier. So whatever needs to be processed in that iteration of a graph algorithm is being encapsulated within a frontier. So if this example was my complete graph, and let's say my algorithm begins at the source node and my source node happens to be this yellow node, that yellow node will be my first frontier that I start the work from. That's the idea of a frontier. And in this data-centric model, any operations that are done are usually just done on the frontier itself, and sometimes the entire graph as well. But you can think of it as the frontier being the entire graph. But the idea is that there are operators. In Gunrock, they are called parallel operators that then process this frontier. And these operators are usually just transformations or traversals on the frontier. So, and this is mainly where most of the parallelism, fine-grained parallelism, lies within the data parallel world. Because these frontiers will have thousands or millions of nodes, and we want to process all those nodes together. And these parallel operators are then customized to be able to process all that work in parallel together. So any questions so far? I'm happy to stop. Okay, sweet. So parallel operators and frontiers sort of make up this this data-centric world that I'm talking about. Gunrock features a wide list of parallel operators. Among them are some like advanced, which sort of traverses, which takes an input frontier, like this green box right here, and then visits all the neighbors of that input of the vertices within that input frontier. So if you have this vertex, we'll visit all of the neighbors and generate a new frontier that's basically consists of all the neighbors of the input vertices. It also features something like a filter where we take a frontier and filter the vertices that we don't need based on a condition. We can do transformations on the vertices, edges, or weights of the graph. We can do something like a uniquify, which removes duplicated vertices within a frontier. And then there are other interesting sort of operators as well. And you can find the complete list of operators on this link. And all of these support parallel operations. So this is mainly where the parallelism lies. So the next part of this presentation will go through looking back at that pseudocode and seeing how that gets mapped onto real-world Gunrock code. And my goal will be to use use sort of a simple operator like advance, which is sort of a traversal operation, and filter to implement single source shortest path, but now in parallel. So rather than with the example we were seeing, which was entirely sequential, we are going to abstract that the components away and look at a parallel version of that. So we'll be looking at some C++ code. So one thing you would notice right away is, or maybe not, but like one thing that is important to point out here is that any code that I show has really nothing to do with CUDA itself. So I am a CUDA C++ programmer, but the goal of Gunrock has been to abstract away all of the GPU programming bits and really just have the programmers look at it from sort of the C++ perspective, or maybe at a higher level, Python level, Python abstraction, where you don't necessarily have to worry about the CUDA bits and just work on the C++ level. So we come back to this sort of relaxed condition that we were looking at in the pseudocode earlier, where the idea was to, given a tuple, so your source, neighbor, and weight, apply some condition to it. So in this case, the condition being, if I found a minimum distance, update my distance. So how this or any condition is captured within Gunrock is using C++ lambda expressions. And C++ lambda expressions are this great general sort of functions that can be applied to pretty much anything. In this example, what I'm showing is that the lambda expression named shortest path, it could be named anything. The device here is a little keyword that you have to use for all expressions that are able to run on CUDA, basically. So it's just one little bit that you have to have for it to run on GPUs. But the rest of it is all C++. So in this lambda expression, what we're doing is we are providing the user with the source, the neighbor, the edge, and the weight. So a tuple that's being processed. And you can imagine in a distributed computing world, every thread in your processor is running this lambda function, is running this computation. So if you have 1,000,000 threads, all 1,000,000 threads are processing a tuple of source, neighbor, edge, and weight, but different source, different sort of versions of this tuple. It could be the same source, but a bunch of different neighbors of it. It could be different sources, different neighbors, and so on. So it's processing this tuple. And once a user is given that tuple, they can define their computation within this within the curly braces of the lambda expression. So in this case, me, the programmer of Sssp, is saying that I want to define my computation to be, give me the current source distance, give me the new distance to the neighbor, and find if that's the minimum distance. And if it is, update it. Otherwise, do not update it. The computation is very simple. It's just Ssssp's if condition being mapped onto sort of the lambda expression itself. And how we execute that lambda, which previously was a for each, a sequential for loop, is using parallel operators like I described. In this case, we are saying we would like to perform advance using this lambda expression. So you'd notice shortest path lambda being sort of sent as a parameter to this parallel operator. So what this is doing is it's saying perform the advanced traversal, which is give me this tuple, source, neighbor, edge, and weight, and apply this lambda to every single tuple that is sort of generated on this frontier. Sort of these two sort of things just capture the entire execution of this for loop and the condition itself. I'll stop here for a second.
So, sorry, what does advance mean? What is it?
Advance is a parallel operator that just says, if I have an input frontier, visit all the neighbors of the vertices within the input frontier.
I see. So it's similar. It's similar to edge, like mapping over the edges incident to this current frontier.
Yeah.
Okay. Sounds good.
And then, do you also add to this frontier, and do you have a remove?
An add. So by add, do you mean do you append this the neighbors to the frontier? Yeah, so advanced generates a new frontier, which is now the neighbors of the original frontier. You can append it, but it doesn't do it with the default mode. No.
So basically, it replaces the frontier. I see.
Correct. Yes. So in the next iteration, you will have a new frontier, which is now all the neighbors of the previous frontier. So this is how it's sort of sequentially doing that. Doing the main iteration, but within an iteration, there's lots of parallelism that it's exploiting that's available within the frontier. So we start with the source vertex, we visit its neighbors, then we visit their neighbors, and then we visit their neighbors, and so on until the entire computation is complete. So let's move on to the next bit, which is simply if a vertex is already visited, remove it from the frontier. So this is more of an optimization, but it's using a filter operator by saying, like, hey, if we have found the minimum distance, let's make sure that vertex doesn't stay in that frontier going forward. So just a simple condition that's saying, take a look at the frontier, see for the vertices that have already been visited, and just remove them. And this is all done in parallel. So every thread looks at the vertex, one vertex within the frontier, and just sees if it meets this condition. And if it does, it's removed. For both of these, so this is the operator that we are executing with the lambda. Again, the lambda is defining the condition for removal. So user-defined condition for removal. I will highlight two more important bits here. One is advance also takes in different methods for load balancing work. So you can imagine one of the source vertex having millions of neighbors, like maybe a social network celebrity that has millions of neighbors, and other vertices that are processing in the same sort of wave as that celebrity might not have as many neighbors. And that could be a lot of load imbalance, right? So this parameter here is defining the load balancing schedule for dividing the work to each thread equally. And there's different ways you would want to load balance as well. And all that is captured within this just one single enum. And my dissertation solely focuses on sort of the load balancing aspect of irregular sparse workloads, which if you have time, I'll get to it. But together with these two operations, we have effectively captured single source shortest path in a parallel GPU world without really needing to do any CUDA programming. And to complete it off, to top it off, we just need a while loop surrounding these two functions, these two function calls that just says, keep doing these iterations until my frontier is empty. And as Kuba pointed out, that maybe the frontiers there will be a new frontier after every advance, which means every advance and filter, which means that there's eventually all the vertices will be processed, all the vertices would have been visited, all the neighbors, all the minimum distances have been found. So it's time to sort of stop that algorithm. And to sort of visualize this whole code, we can look back at the bulk synchronous programming model diagram I had. The idea being, we start with a frontier of some nodes, of source node baby. We do a traversal, so generate a new frontier of its neighbors. Then there's a synchronization step. This is why it's called bulk synchronous, because it's processing things in bulk and then synchronizing. And then we perform the filter operation in sequential. So these two operations are sequentially scheduled, but internally they are all parallel. They're doing a huge amount of parallel work. And then they loop until a certain convergence condition is met. And that sort of entirely captures our single source shortest path algorithm. And if you're interested in seeing the complete code, it's available in the link below. So yeah, this slide just summarizes what bulk synchronous programming model is. It's a series of parallel operations separated by global synchronization calls, and with a loop, and they loop until a convergence condition is met. The next bit will be sort of shifting towards sparse linear algebra world, but this is sort of a side project that I attempted, which was let's take a look at, we have seen sort of how Graph BLAS does graph algorithms, where it represents graphs as sparse matrices and then performs operations like sparse matrix vector to implement graph algorithms like breadth first search, single source shortest path, and so on. What if we do the reverse of that? Because this duality of graphs and sparse matrices exists, can we implement sparse linear algebra using data-centric graph operations? So this is just a simple example to look at that. And the reason why I would like to show this example is because if you notice, it uses the same parallel operator as we implemented earlier. So with a single parallel operator, I'm able to implement SPMV. I'm able to implement single source shortest path. I have used this traversal operator in breadth first search, PageRank, and many other graph algorithms as well. So the beauty of this is that these parallel operators, once you have identified sort of a subset of them that you need, you can implement a variety of graph algorithms and look at a variety of sort of problems. In this case, what we're doing is implementing push-based sparse matrix vector multiplication, where now I'm doing the exact same lambda expression. It's giving me the exact same tuple, source, neighbor, edge, and weight. But instead of considering them as source, neighbor, edge, and weight, to me, this means that source is a row index in a sparse matrix. Neighbor is a column index. Edge is sort of an ID that represents this pair of one row and one column. And weight is the non-zero at that entry. I'll go back a little bit. I should have added a figure. But if you look at it here, so if my source here is 2, my neighbor here is 1, and this black dot is the non-zero that I care about in the SPMV. So now I can use this duality to do sparse matrix vector multiplication in data-centric model. It uses the same advanced operation that we saw earlier, which is the traversal. But instead of doing some work on the distances or finding the minimum distances, which was our previous condition, we're now doing this atomic add, so accumulate add, basically. So the operation that it's doing is written in the comment here. So it's doing y plus equals weight times the value in the dense vector x. So pretty simple way to represent SPMV in using some of the data-centric models stuff that we have looked at. The next example is sort of the same SPMV example, but done using a pull-based traversal. In this case, it's now using neighbor reduction instead of the advanced operation that you saw earlier. And all this does is, instead of doing an atomic add, we remove the atomic and do a reduction, a segmented reduction over each row of sparse matrix. So implementing the same algorithm using 2 different methods, push and pull-based traversals, which some of you might be familiar with the push-pull BFS work by, I'm forgetting the name, but there is push-pull BFS. Yeah, the next example is just showing how one can do SPMM instead of SPMV by adding another loop that goes over your dense matrix. So just a minor modification of SPMV to do SPMM. I'll quickly move over from that. So what we have seen so far is an example of bulk synchronous programming model. But there are other programming models that exist. Namely, there's an asynchronous programming model for graph analytics as well. And this is something I'm experimenting with within Essentials and Gunrock, where Gunrock isn't necessarily limited to BSP. And the reason why that's the case is because we can change the underlying data structures of how things get stored in a frontier, or how a graph is represented for a certain graph representation. And because of that, we can, for example, we can take a frontier and represent it as an asynchronous queue, such that as work is being generated, it's being pushed onto the queue, and threads in parallel can then take the work from the queue whenever they need it and process things asynchronously, rather than doing this large parallel operation and then synchronizing, we are now implementing an asynchronous queue that can just take the work from this queue and process things asynchronously. So this is sort of an experimental feature that I'm considering and working with. Any questions so far regarding the BSP stuff or async stuff or graph BLOS things that I should?
So I would be interested in like some performance comparison. So specifically, I mean, as I understand, the motivation behind asynchronous is that it may be faster than the synchronous model. So do you have any results on that?
So we just recently published a paper in SC. Actually, it's under review right now. It's submitted to SC, but I am not able to show the results right now, but I'm happy to send you a copy of the paper afterwards, which does this comparison of BSP and async model and how algorithms compare. In fact, it does it for multi-GPU space.
And then, like, is the TLD, what's the TLDR like?
So the general conclusion of that is that asynchronous is really good for small frontier problems where frontier relatively stays regularly sized, and it's really good for that problems. But scale-free problems or power log problems are mainly still beneficial if you do sort of this bulk synchronous programming model approach. The other benefit we found was with an asynchronous queue, load balancing was really, really good because work was being processed and added, and as threads needed more work, they can just queue for it. So the overhead for load balancing was hidden behind sort of this asynchronous queue work rather than explicitly adding a load balancer on top of BSP parallel operators. That's sort of the TLDR. And that work looked at, I believe, breadth first search, page rank, and algorithms such as that.
What can you say a little bit about the scheduling policy you use when you're pushing work to these asynchronous queues? Like I know, for example, Galois, there's been a bunch of work, both on theory and also like I guess the Galois folks are concerned mostly with practice on, maybe using like randomized push pull, right, to sort of give good load balance.
Yeah. So yeah, for asynchronous in specific, there's a number of ways that we have sort of experimented with it. Yushin, who is the lead author, can obviously comment on that better. But the idea being that each thread within the GPU, sort of each block, has a segment within the queue that it's sort of locked to, and these threads sort of process the work within that queue. The idea being you don't want to go beyond the segment for your block, so that you're not tapping into other threads' work, because that's an expensive synchronization cost. So between blocks, it's quite expensive. But each thread doesn't take a single work unit. It takes like a chunk of work from the queue and then does a static scheduler on that chunk within its sort of its local computation. So it pushes work in sort of singular manner, but it fetches work in this sort of chunk manner, so it can statically then schedule the work to the underlying threads, or the block and then schedule the work to the underlying threads. And I'll get to load balancing a little bit more if that's interesting.
Yeah, I just also wanted to mention there's this researcher Dan Alistar. He has a bunch of interesting papers on like the theory of these like asynchronous queue-based algorithms, showing that you can actually get work-efficient algorithms in some cases.
Yeah, I would love a link to that actually. Sweet. So just to sort of summarize the Gunrock sort of space and Gunrock graph algorithms, these are some of the graph algorithms that we have looked at, and you can find pretty much all of them here with sort of links to where they're implemented. But there's a wide variety, and we have looked at 30+ algorithms now. Includes things like Louvain clustering, connected components, k-nearest neighbor, breadth first search, between-us centrality, graph coloring, and so on. And some of these we have experimented, like graph coloring, we have experimented in both sparse linear algebra world and graph algorithms, data-centric world. Sorry, go ahead.
I have a question about the abstraction. So to what extent, like was this all possible using a single abstraction, or do you sometimes need to, like, for some of those implementations, go beyond what's there in the API?
So that's actually a great question. So part of our Hive project was discovering where the limitations of this abstraction lied when we were given real-world graph problems to implement. And what we found was the single most useful thing was being able to capture general computation within a lambda expression. So DARPA came to us and was like, we would like to do this graph algorithm, but we want to do this one extra step within that algorithm. Like maybe you're updating a string, maybe you're capturing something else. But since things were implemented using C++ lambda functions rather than some DSL sort of approach, we were able to capture all of that within our current abstraction. So we did implement new operators, but that didn't fundamentally change our abstraction. It was just like, hey, this is an interesting graph operator that we would like to have to do more algorithms. And we added that, but it didn't change how the abstraction truly worked. So these lambda expressions are actually quite powerful. So powerful that Graph BLAS community is now considering adding them in their C++ APIs, for example. So if the best example I can think of is I implemented geolocation, which is a geotagging algorithm. And the idea was you have a graph of a bunch of sort of, let's say, social network sort of users. And you would like to geotag the ones that didn't have location information, right? So it was a graph problem, but I wanted to operate more than just on the graph. So the latitude and longitude of the users, for example. And that extra information can now easily be captured within a lambda expression. I can go ahead and type, hey, take this array latitude and longitude and index it using my source or neighbor IDs or edge IDs. I was also able to do problems like NetFlow, so network flow problems in a similar fashion, where the IP addresses or things that I related to IP addresses, I can now update and capture within these lambda expressions. The only thing I would say that truly challenges this model is our dynamic problems. So dynamic graphs are really, really hard to do on like period, but on GPUs, they're extremely hard. And it's a work done by Mohammed Awad, one of my colleagues, who has looked a lot at dynamic data structures on GPUs. And that's something that's very interesting to us. We have an implementation of a graph representation that does dynamic graphs using GPUs, but it is bulk dynamic updates and deletions, not necessarily like singular things. And that's the closest. That's the only thing I would say that challenged this abstraction the most. Yeah, so this is majority of my presentation that I wanted to sort of give here. This sort of slide summarizes the entire program stack of Gunrock, where we have external hooks or examples of external hooks into Python, C++, and Rapids is NVIDIA's cuGraph library, which also internally calls Gunrock or has some algorithms like hits using Gunrock's implementation. And Rapids cuGraph is also built on our abstraction and our research work. So we are in very close collaboration with NVIDIA on some of this stuff. And then you have the underlying algorithms layer. Then you have the programming models and how they get mapped into operators. And then the last is the hardware backend, which right now mainly targets CUDA C++. I do have an implementation targeting C++, parallel C++, so parallel algorithms within C++ using Intel's TBB. But that's just more of an experimental like project thing rather than an actual, actual part of Gunrock. Let's see. Yeah, I'm gonna sort of go over that. Yeah, you can find the links to Essentials, which is sort of the GPU implementation, and the last node I mentioned, the CPU project here. Gunrock is sort of the GitHub link for the main library. I don't know how much time I have. I have some slides on load balancing stuff if you're interested in that, but I'm happy to just stop here and take questions and maybe.
You have time till 3. So.
Sorry, I didn't catch.
You have time till 3 p.m. like 15 minutes.
Okay. up to you guys. If you have questions or we would want to have a discussion on this, but I'm happy to take more questions first. And then if you're interested in performance stuff, I do have performance numbers from the load balancing side. So the graphs I have mainly focus on SPMV things. But we have a web page with a very in-depth analysis of Gunrock's algorithms being compared to other libraries as well.
Yeah, I have a question about how the abstractions work that you describe work when you can't cast the problems as SPMV. So, for example, for maybe the most efficient implementations of connectivity, or maybe even some like more complicated problems, like some of the problems that folks want to solve in practice on graphs, or maybe involve clustering.
Yeah,
and it's not really clear how you can express some of these problems. And I could give some more specifics as SPMV. So do you have some?
Yeah.
Have you encountered such problems in the Hive work, or can you say something?
Yeah, that's a great question. So the operators, the parallel operators that I mainly discussed today were centered around problems like SPMV. But there's definitely problems that don't necessarily map to those operators at all. And some algorithms in this list do not use advance or filter at all. Some of those problems are like shared nearest neighbor, which is sort of a DB scan kind of algorithm that encapsulates sort of density in mind as well. And the idea behind that is we have other operators like set intersection, set union, and things like that are able to then capture more algorithms that don't necessarily map to just SPMV. The clustering problems, we are planning on adding a pointer chasing operator, a parallel pointer chasing operator that's able to sort of, right now it's done using a parallel 4. If I go back, let me see if I can go back to the list. Yeah, there you go. Right now it's actually done using a transform parallel 4 operator, the pointer chasing aspect, but we have an implementation of a pointer chasing parallel operator that is able to implement connected components, for example. And I think it's used as part of Louvain clustering as well. I'm not exactly sure on that. But yeah, there's definitely problems that don't necessarily map onto the first two operators. And that's why we have this list.
Thanks.
And these things did come up a lot in Hive. One of the computations, another computations that we saw was sort of this neighbor reduction. Although this is somewhat of an SPMV kind of problem, the idea being you take take the neighbors that you have traversed, and then you want to do some parallel reductions on that. That was a very interesting sort of computation that we saw that appear in real world problems as well. The things like triangle counting is implemented using intersection operator. Yeah.
I have other questions, but I don't want to. If anyone has other questions, please feel free to ask.
I mean, I would be interested to hear something about performance, but not sure like how much time does that require.
I can show you some results. Let me see.
Yeah, my questions are also related to performance. So,
well, go ahead and ask a question. Maybe I can pull up some of the performance analysis numbers.
Yeah, so I'm curious to hear your thoughts about where GPUs are going, right? So NVIDIA has these releases where they sort of double the bandwidth, double the cores or warps.
Yeah.
And what are we going to be programming in 2, 4, I don't know, 10 years, right? Are we all going to be GPU programmers? I'd love to hear your thoughts on.
I think that's a great question. So I would say I don't necessarily agree with NVIDIA's approach of adding sort of more compute units, and then the memory bandwidth is just sort of scaled along with it. These problems are entirely memory bottlenecked, so memory bandwidth bottlenecked. And the solution to that isn't necessarily adding more compute units. That's really not solving anything for graph analytics. It's mainly for gem operations. And even that is reaching its peak. So we have a work published called StreamK, which is a scheduling algorithm that targets scheduling for for dense linear algebra. And the kind of the idea of stream K that we show is that reaching 100% peak throughput of a GPU, even for GEM problems, has become harder now. And we propose a new scheduling algorithm that's sort of able to address that and compare it to cuBLAS and cuDNN and Cutlass and show performance improvements that are truly astonishing compared to some of the heuristics that cuBLAS uses and completely fails. And that's largely due to the fact that NVIDIA has made their devices wider and wider. I think for graph problems, at least in the GPU world, there has to be a solution somewhat comparable to what they have done for ray tracing, where they added a ray tracing unit to the GPU itself. So it's an accelerator for ray tracing, and it just accelerates sort of the BVH tree computation. So for graph algorithms, to me, that would look like accelerating the underlying primitives used to implement like the load balancing aspects and things like that. And that includes parallel scan, parallel reduction, some sort of accelerators that are able to capture memory operations or in-memory computations within this sort of GPU world. And how one can go about programming these, one possible way is to rely on C++ parallel algorithms, which are now looking to support CUDA as one of their underlying execution policies, which is a really cool way to do that. Or these frameworks that sort of abstract away some of this CUDA programming. I think DSLs like Graphit are also a really nice approach to this. But to me, it doesn't seem like you don't necessarily have to be a CUDA programmer, but it doesn't seem like there is right now that bridge is being fully sort of captured, besides the formal efforts by C++ that I see, which I don't know if I entirely agree with, but still that's something in that direction.
Sorry, but by DSLs and stuff, are you also referring to like this Intel 1 API and stuff like this? Right?
Somewhat, yeah. I'm not as familiar with the 1 API stuff as I am with like I was mainly talking about Graphit, the MIT's Graph DSL. So more parallel domain centric sort of DSLs rather than like a one abstraction that covers all of them. I'll quickly pull up some graphs so we can maybe look at just so it's I did not include, because I've wanted to focus more on abstraction in the API, I didn't include some of these results in the actual presentation, but they're all available on the website. Very handy. Hopefully you're able to see this web page.
It's a bit too small, but if you decrease the window size, this would get bigger.
Does this help?
Yeah, it's visible here. Not sure about.
Yeah, it looks good.
Okay. So the methodology we use for measuring performance is edges traversed per second or runtime. So in runtime, we're mainly talking about for most stuff, we're talking about in milliseconds. So we process things in extremely fast sort of milliseconds way. And the kind of data set that we look at is Sweet Sparse Matrix Collection by Tim Davis, I believe. So lots of sparse matrices in that, lots of graphs in that matrix collection, and we compare our performance to all the different frameworks that exist. So let me go ahead and actually quickly go to that.
So what was the result that took like what 20,000 milliseconds, so 20 seconds?
So this right here Asia OSM. This is running in this is running like in Asia OSM. This is how many vertices? How many? It's like 11 million vertices, but 25 million edges. But it could be part of it has to do with the kind of data set that you're looking at. So this is looking for BFS problem, and a lot of it can be extremely different performance characteristics for other different problems. But this is looking at some of the like 25 million edges, 11 million vertices,
I think it's a road network graph. It's OSM.
Yeah, road network. Like entire Asia's road network or something.
It's just ultra sparse, and you have lots of fine-grained frontiers to handle.
And part of the reason why some of the other ones are really, really fast is mainly due to how we load balance these sort of graphs. So a runtime comparison is one of the main metrics we look at. The other is edges traversed per second, kind of like a throughput-oriented approach to seeing how much you can process. And this sort of performance analysis page captures, I think, 4 or 5 main algorithms like PageRank, between centrality, single source shortest path. Since we've been talking about single source shortest path, we can take a look at that. Let me see.
So what's MTEPS?
It's millions. So it's edges traversed per second, basically. So MT is, let me go to methodology. Let me go. So it's throughput being measured as edges traversed per second. So M just means millions of edges traversed per second. So the order is in millions. And the other methodology we report is using runtime. It's just how fast a certain algorithm was. But together, they sort of capture the whole sort of landscape, I believe, and just how fast things you can process and how much things you can process within given a hardware architecture speed of light bottleneck. It's a nice way to see like how far away from roofline you are, for example, for like a GPU hardware, for example. Anyways, this might be, a crude way to look at some of the results, but if you would like to do this yourself, it will probably be a bit nicer. A lot of this webpage gets periodically updated as well with new results as we make performance improvements.
So I'm curious how you go about like doing performance engineering. Like, how do you know? Can you say a little bit about, as a GPU programmer, how you know when you've gotten peak performance for a problem?
I think that's a good question. There has to be like a point where you just know to stop, know when to stop, kind of. You can definitely over-engineer some of these things. I like the talk by Stephen Jones on some of this, where if you can get to within 80% of peak performance, and peak performance usually means like speed of light performance compared to measured using, let's say, the roofline model or something equivalent. If you can get within 80% of your way to that peak performance, you have mostly done a great job at performance optimizing the problem. The last 20% can take absolutely enormous amount of time to sort of sift through. But it's generally what I have done in my work is create sort of a load balancing abstraction that makes that bit easier. I'll go and quickly show you some of the performance graphs I have for load balancing stuff. The idea is that there is different ways to load balance your graphs. So this is the same sweet sparse matrix collection on like 4,800 matrices, 4,800 sparse matrices, looking at the results for 2 load balancing schedules. So the purple is an explicit load balancer, and the yellow is sort of implicitly just relying on the structure of the matrix itself. And as you can notice, there's lots of yellows that are underneath the purple, which means that there wasn't any need to load balance them in the first place. The problem was very nice, structurally balanced already. And this shows up in graphs all the time. Like there's some graphs that are just naturally nicely like structured, whereas others are just like a mess in terms of scale-free graphs. They're very, very imbalanced. And you can use like, for us, we generally rely on studying the structure of the sparse matrix to figure out what kind of scheduler would work the best for that. That's the main sort of approach that you can take. You can apply common techniques like kernel fusion, use crashpad memory the best possible way you can, and just general optimization techniques to sort of get more out of it. But most of your performance lies in load balancing. So my goal has been creating a load balancing abstraction and implementing a bunch of load balancing algorithms as like a contribution that you can then play around with by changing a single enum and just quickly see what your performance looked like for your given problem for a certain load balancer. It sort of bridges that gap of going about optimizing these really irregular sparse problems. And in this graph, the graph, I was just playing around with different heuristics to see which one to pick from and how you can achieve sort of good performance versus if you were given perfect heuristics, for example. So blue is perfect heuristics. Black is something I was playing around with. Yeah, and I don't think I have a lot more than that. If there's any more questions.
Thanks for the nice talk.
Thank you for having me.